So I'm Paul Wren. I'm from Arizona State University. My partner in crime is Ron Febick from the University of North Dakota. Ron's primarily a small bodies guy, but he was my advisor for my master's. And so he and I have been taking on some kind of hobby level research projects, hoping to then later stitch them together into something much bigger, but we'll see what we can do with that. So I want you to notice preliminary and promising is the subtitle of our talk. We're still in the early phases of data collection and classification. So I'm just gonna get moving here. And of course, my keyboard's not responding. Okay, so doublet craters, what are they? These were seen in the 70s in lunar images, in Martian images, originally thought to be the result of atmospheric breakup of incoming impactors. Didn't make much sense on the moon though. Tidal forces were also proposed as reasons, but ultimately everyone decided that the widely separated nature of these twin impactors that are hitting at the same time could not have come from any of those other modes, and that it's well established now that they're formed by well separated binary asteroids. In the upper right corner, do I have a pointer? I don't know, maybe I can make a pointer. I should have tested this, doesn't matter. In the upper right corner, you see a really beautiful doublet crater that's on the Martian surface. You can see the characteristic septum that's created between the two craters where the crater walls collide with one another. And of course, all of that ejecta that's being flung from one crater toward the other collides with the other crater's ejecta, and you get these kind of really cool ejecta lobes at right angles that throw additional ejecta in those lines you see parallel to the septum. So that's a very characteristic and thank goodness, very fresh, relatively speaking, doublet on Mars. The other images, there's a doublet at the bottom from Ceres that we actually first located, and that other one is on Venus. So they pretty much everywhere there are impact craters, I suspect we'll find doublets. And in general, the observed percentages of doublet impacts across these various bodies kind of hint at about 15% of the inner solar system planet crossing asteroids are likely to be binaries. Okay, I gotta keep going here. So we wanted to look at the moon. Ron had done some preliminary work years and years ago as a class project at his unnamed university, and we used that as a kind of a framework to go redo that work using some of the latest imagery and other data sets. So we want to try to see what we can learn about at least the historical asteroids that were crossing Earth's orbit and therefore the moon's, in terms of how many of those may have been binary asteroids. And of course, we're using craters as a proxy for binary asteroids, and we're using the moon as a proxy for impacts that might have happened on Earth but have since been erased. Okay, so data sets we used the very, very nice LROC WAC global mosaic for initial look-see. Then when we really needed to focus in on a small pair of craters, we would load up individual NAC images, nice high-res images. And just in the last year, we've been able to host on JMARS. I think it might be 1 or 2 years old. USGS provided this to us. It's a blended elevation model from Lola and Kaguya. Gosh, I hate it when I get phone calls while I'm talking. Anyway, from the terrain camera on Kaguya, it's a much nicer than just Lola alone elevation model, and we use that for looking at elements of crater morphology. So we chose 5 Maria to study they're spread out quite a bit so that I couldn't even get humorum itself outlined on here, but you can see in the lower left there, it's just around the corner. We looked at these 5 because they were, we wanted Mare in general for being lightly cratered, not saturated. We also wanted uniform surface ages in general, just to kind of remove certain variables. And we wanted to use surfaces that were sufficiently far away, hopefully, from the larger, newer impacts on the moon that may have, inundated some of these layers with secondary craters. And by the way, I'll just note right now, we chose, for simplicity's sake right now, to draw rectangular search areas within the Mare. It's just much easier for this first go. We'll look at possibly creating an exact shape that matches the uniform surface in a later attempt. Back in 2018, I did a study with Ron's help on Ceres, looking at doublet craters there. Our approach is going to be very similar. We're using the same basic steps, the same scoring system, well, but with a couple of notable exceptions, which on the next slide, I'm going to note them. This time, we're lucky enough to have the Robbins Lunar Crater Database. Thank you, Stuart. And we used it in JMARS to locate the craters themselves. I'll talk more about that in detail. Also, we are only examining potential pairs that we think we can make a good case that they really are doublets. Clearly, doublet impacts can be so well separated that there's a good distance even between their rims, but it's kind of hard to prove your case without additional evidence, like maybe a septum, maybe they're so close together they form two low points in a peanut-shaped crater. So we're not going to deal with anything other than craters that at least touch or overlap. Okay, so I'm going to go real quickly through our methodology that we use for this, mostly because this is what I have to talk about. We haven't gotten to any deep analysis of our results yet. So I want to talk about this and also use it as an opportunity to plug JMARS 5, the new version of JMARS, and how it was used. So I hope you can see on the diagram the green dots and circles that are in this area. That's the result of doing a query on the Robbins Lunar database, crater database. So instantly, I have all the craters from around 1 kilometer and up already located within the search area. I think this is Chrissy, yeah. And then we can then almost instantly export all of those identified craters to a CSV file. We get like, the lat long, and we right now are only getting the diameter. There's a lot of other good metadata in there, by the way, that's available and viewable in a table in JMARS. And then we use a Python program that reads that CSV, creates the candidate pairs using, just some simple arithmetic to identify the pairs that touch or are even overlapping. And we also create this cool custom shape layer with polygons. They're really just lines that we can import back into JMARS to do the searches. So that's what this is. That custom shape model gives us the ability in a table to scroll through pair by pair using those are the crater numbers. And right on the screen, we just draw a line between the centers of the craters as specified, by the Robbins database. And we can reposition to each pair of craters one at a time and then do our analysis. And that's where humans come in. We don't have any sort of a automated system for scoring these things yet. I said yet, we'll see. So this also allowed us to do the work kind of as painlessly as currently possible in terms of doing the individual analysis. And our scoring, I'm not going to go into the details of the scoring, but I could, but I don't have a slide for that. We add points to our score for a crater pair if they have similar erosion, meaning they look about the same age to our eyeballs. which could still be, a decent amount of time. But is there a septum? Maybe a septum. Are there ejectolobes? Those get you positive scores. But then if it's clear that the craters are one superimposed over the other, it's out. That's actually a big negative. If they have differing erosion, negative. And then we use the 3D view to see if their depths in relation to their diameter give a reasonable profile indicating they would have had the same impact velocity in spite of one being bigger or smaller. But again, that's at this point, that's kind of a rough eyeball estimation based on the 3D profile. And by the way, this crater right here, pretty sure it's in Tranquillitatis, for these two craters. You can see there's a septum between the two and ejectolobes extending out up and down from those two craters. That got a score of a +5. The vast majority of crater pairs we inspect actually get big negative scores. Okay. One other thing we've been able to do, and we plan to use it extensively to finalize our scoring and analysis and acceptance of craters as being true doublets, is this new radial profiling tool in JMARS. It allows you to select a crater in the crater counting layer, and then you just open up this profiler viewer, and all of the lines in your profile get graphed on here. It's an easy way to kind of review the data. You can then export that to a CSV file, which we do. We're planning to then programmatically import those data. They come out in a nice big spreadsheet with elevation data at each point along the way at whatever resolution. Here we were using, this is on SERI, so we were just doing the relative elevation for an oblate spheroid. You can change the number of lines. I think you can go up to 20, and you can change the length of the profile line to be shorter or longer based on a percentage of the diameter of the crater. And then in the lower corner there, you see the 3D view that lets you, on the fly, kind of using your cursor, tip and move and rotate the actual profile of the crater in 3D. Really, really useful for getting an instinctive feel for what's going on. Intuitive is what I mean. Okay, and don't forget, you can do all these things in JMARS. So that's my last JMARS point. So let's take a look at some of what we've found so far. These are some examples of likely or definite doublet craters on the moon. The first one is a peanut shape. That is two impactors that were so close, you really only have one rim. Also, the one we just looked at on Tranquillitatis. Here's a nice one in Serenitatis with a nice looking septum. By the way, when we look at these, we look at different lighting to make sure we pull up the 3D profile. This is a nice straight septum. You've got some kind of erosion, probably a lot from maybe some micrometeorites, but it's still pretty clear. Sadly, it seems that the ejectolobes disappear pretty quickly, but there are some hints. There are some hints there. Okay, next slide. Here's some more. Only found one in Humorum, another peanut in Serenitatis, and then this I'm saying because when I first found this, I thought, oh yeah, that's a good one. But it's missing some of the fundamental characteristics. They're far enough apart that they're maybe just barely touching their rims. There's no septum. And I'm curious if any of you, maybe when we get the discussion, think about that crater. See what you think. Is it actually a likely doublet? I know that you could have two coincident craters that happen probably 1,000 years apart, and they might look to have the same age. So this is some of the problems we're up against. Okay, so the current status of where we are, we have found a few doublet craters. We have not yet finished processing Fecunditatis. If you notice, Fecunditatis has 795 candidate crater pairs within that area, and certainly the most number of individual craters as well. We just have a long way to go yet to go through that one. We did wrap up Tranquilitatis before this meeting so that we have some stats. So my next slide is that same table without Fecunditatis so that we could actually do some simple percentage computations. The problem is these are just way too low from everything we're seeing in all of our other surveys. We've done Vesta, we've done Ceres. Other people have clearly done Mars. These are just low, possibly by a factor of 10. But of course, what we've all talked about, and we've been talking about the last day and a half, is our friends on the moon, which are those secondary craters. So we get this percentage of doublets out of total impact events by dividing the doublets by the total number of craters in the study area. And I have a strong belief that in this number of 3,500 plus individual craters, a large, very significant percentage are probably secondary impacts. Certainly look like it in Tranquilitatis. So that's the big problem. What it means is we can't even really say anything yet about what we're seeing until we can deal with those secondaries. We care about secondaries for doublets too. Some could even make the argument that really pretty doublet that I found with the ejectolobes and septum may in fact be a secondary. We're going to have to look at that in a lot more detail, and not just at the candidate pairs, but at all the craters in the study area. Okay, so what's next for us? Obviously, first step is complete the candidate pair analysis in Fecunditatis. We have to wrap that up to get our full data set. And then a big kind of side detour we need to take is trying to pull together, evaluate, and maybe even create some techniques to discriminate between primaries and secondaries. The secondaries are there, we can't help it, but we want to just kind of ignore them for what we're doing for both the total crater counts and doublet impacts. You get some really nice looking doublet impacts from secondary craters, because guess what? They're impacting at the same time. They can be along a vector where they're close to one another. So that's a huge issue for us that we have yet to deal with in this data set, where it sure looks like there are a lot of secondaries. Now, once we can do that, then we need to go and determine our percentage of primary impacts, just to kind of see how it matches up with actual observed current near-Earth asteroids in terms of binaries. And we also plan to run Monte Carlo simulations, as we have in the past, on the areas, producing random impact locations, and then analyzing those results against our actuals to see if there are, and by actuals, I mean the actuals of just the craters, irrespective of whether we think they're doublets or not. We want to see if we bin the separations between all possible pairs of craters in both the Monte Carlo sim and our actual craters, if we see any exceedances in any of the bins that might indicate, we had a statistically significant difference in terms of extra craters at various separation sizes that are in that bin, and maybe indicative some additional support for them being actual single event impacts. One event, two bodies, creating a visible doublet. Okay, well, that's about it. I have a thank you slide and a quick summary of everything, so we can keep that up during questions. I have a feeling I took like 3 minutes because I feel like I just blasted through it. I don't know, what's the timer say, Lillian?
That's all right. We've got about 5 minutes for discussion and questions, and we can always come back during the discussion section to talk about this.
Sure.
So we do have a couple of questions in the chat window. So Stuart, I'll let you control that. Oh,
sure. So I'll just note real quick, yes, there are a lot of secondaries in my database for the moon. First question from Paul Schenk. Can we be sure a later impact would not produce a false septum, which would be difficult to recognize as such after significant degradation?
I would say I've looked at a lot of crater pairs, and when it's not, the real septums just are not straight. If I'm apparently sleep deprived, I can't finish a sentence. That basically the septum won't be straight if you have a subsequent and what I call a superimposed impact. That crater that comes in later says get out of the way and typically pushes a crater out of the way. I think the only place where we could mistake a coincidental impact is the situation I was talking about, where the rims are right next to each other. I do know that Jordan Kendall at Goddard has been doing some simulations of secondaries in ISAIL, you know, some hydrocode stuff. It's worth me talking to him about that to see if he has done simulations where he can come up with things that look like doublets that aren't, you know, through separate impacts. I don't know. Can you even do that in ISAIL? I guess you can if you're simulating a doublet. I don't know. I don't know if that answered everything for you, Paul, but.
Yeah, I would just agree that it's usually obvious, but of course we have to be careful of the toupee fallacy. Cassie asks, have you considered looking at thermal or radar data to see if there are signatures of ejecta parallel to the septa that are not visible in the camera data?
Oh, that's awesome. You know, that idea just from the thermal popped into my head, that yeah, you could see things that are just made of a little bit different composition, different particle size. When we were looking at the earlier work on just the crater counting for age over in Oceans. Yeah. So that's terrific. I have to write that down before I forget, but thank you. Radar and thermal. Heck,
Right,
I guess you could look at spectral too, right?
You could look at anything.
Yeah.
Kelsey is next. She has to be unmuted. It looks like she is, so she can ask her question.
Okay.
Hey, great. Thank you. It's Kelsey Singer. I really enjoyed your talk, so thanks. And I had just a couple of thoughts that I'd be happy to talk to you more about later, but myself and a student have been looking a lot at the ejecta of secondary craters. And we mostly see more directional, like downrange, and as I'm sure you're familiar with. We didn't look specifically to see if we see things more straight out to the side, but we'd be, you know, it might be interesting to do a comparison there. And then also on Pluto and Charon, believe it or not, we have been looking for the signature of double impacts. And so it'd be interesting to talk to you about that too.
Oh, that sounds great. I'll shoot you an email later. I'm sure I can find it. So.
Yep, no problem.
In fact,
I'll share it with you.
I think that it's on your probably on your Google Scholar profile. So.
Sounds good. Thanks.
That's great. Yeah, these would be
Okay.
great.
We have one more question. This is from Romina DeSisto. Sorry for pronunciation. Very interesting talk. Thanks. How can you ensure that the double craters come from binary asteroids? Wouldn't they be more likely to come from asteroids that have been fragmented by tides before the collision? In other words, not necessarily the components of a binary asteroid could fall in the same place.
And I think what you're getting at, there's been some new, I just read a paper this last week. I think they're called asteroid pairs or asteroid groups, where they're in their own solar orbit, but they're traveling together, at least for the moment, because they're remnants of a collision. I can't see you, so I can't even see the chat for some reason. Is that what the questioner is getting at?
Maybe. I think it's more just general. There could be other sources. It doesn't just have to be a binary. It could be fragmenting instead. So it could have been a single body that then fragmented very soon before it struck. But also you have cases where it seems like it doesn't just have to be that, or you might not necessarily just get a binary asteroid forming these close pairs. You could get them very widely separated.
Sure. Well, I mean, keep in mind that even the smallest pairs we've looked at were at or above a kilometer in diameter. So that means if the rims are touching, they're a full kilometer separated even at that point. And we've seen much bigger ones. And I'm certain there are even larger separations than that. You're absolutely right. The funny thing is that most of the binary asteroids we're seeing today in the main belt or near Earth population are actually have very small separations that would create what looks like a single crater. And you're right, there are uncertainties here from top to bottom. All we're hoping for is to have a decent amount of confidence about the ones we do find. Yeah, these are all valid points for sure.